hello, good morning. How are you all? Perfectly fine, very good. Alright, we have started contour integration, and in the last video we have also done one example. It's just a simple step solution. You just have to find out the poles and check whether the poles lies inside the circle or outside the circle. And the poles which are inside the circle, you just have to find out the residue of the function at that poles which are inside the circle, and at last you have to apply the Cauchy residue theorem. That's it, right? And I hope you are going through the examples, because in this assignment I'm going to start the another kind of an example. So it's very important to revise the previous videos side by side. Thank you. All right. There are some remarks. If f is an even function, then the integration from minus a to a fz dz is equal to twice the integration from 0 to a fz dz. Right? This minus a to a changed to 0 to a and twice the integral. Then second is, if f is an odd function, then this integration is 0. Right? Third is, this is important, the integration from 0 to 2a fz dz is equal to twice the integration from 0 to a fz dz if, but you have to check the condition that the function at 2a minus z should be equal to function fz. And if this f of 2a minus z is negative of fz, then this integration is 0, right? Fourth is, if the integration is from 0 to a fz dz, then this is equal to 1 by 2 of integration from 0 to 2a fz dz. Again the same condition, if the function at 2a minus z should be equal to f of z. Otherwise, if it is negative of f of z, then this integration is 0. Fine? Alright. And most of the cases, whenever you find cos in the integration, the cosine in the integration, then this integral will change to, this condition is well satisfied for all the cosine function, and you can change the limits for this integration according to whatever limit you want in your integration, right? Next example, evaluate the integration from 0 to pi 1 over a plus b cos theta d theta, where a is strictly greater than b is strictly greater than 0. Now whenever we have to start the integration to solve this, we have to first ensure that our limits should be from 0 to 2 pi. 0 to 2 pi is your complete circle, and then only you can apply the polar form z equal to e the power iota theta. So limits should be from 0 to 2 pi. But here the limits are from 0 to pi. So I need to change this limit. For that I need to check the rule first, that f of 2a minus theta should be equal to f of theta, right? Here a is pi. So f of 2 pi minus theta should be equal to f of theta. Let's check. Now our function is 1 over a plus b cos theta. I am checking this. Put instead of theta cos of 2 pi minus theta. Now this is again a plus b. Now cos of 2 pi minus theta, we all know that this is equal to cos theta. So this is cos theta. So you see that my function is, again I am getting back my function as 1 over a plus b cos theta. That means f of 2 pi minus theta is equal to f of theta I am getting. Fine? Alright. So now can I change this limit? Yes. So from 0 to pi, you again check your remark. From 0 to a is changed to 0 to 2a, but you have to divide by 2. If your limit is from 0 to 2a and you want 0 to a, you have to multiply with 2. but I always want my limits to be from 0 to 2 pi or 0 to 2a, right? So I need to divide by 2. So here the limits are from 0 to pi, I need 0 to 2 pi. So I am dividing this integral by 2. And rest, this is a plus b cos of theta d theta. Sorry. Now next is, now you can apply your polar form, that is you can put z equal to e the power iota theta now here. Now z is equal to e the power iota theta, and from here you get d theta to be equal to dz over iota z. Putting these values into this integral, 1 by 2 integration 0 to 2 pi 1 over a plus b. Now cos theta will be changed to, I have also in the last video I have also taken this as your remark, that cos of theta is equal to 1 by 2 z plus 1 by z. So this is 1 by 2 z plus 1 over z. It is changed in this, and d theta is dz over iota z. Clear? Alright. Just calculate this denominator and you will be getting 1 over iota and this integral, after putting the value as according to polar form, you have to write this as integral over c, right? Because 0 to 2 pi are the limits for the theta, right? Because now you have changed this format into whole the function is in z. So here you have to mention the circle, see the contour. So this is 1 over bz square plus 2az plus bdz, right? And now you have to take whole this function as f of z. So this is equal to integral over c, integral over your circle fz dz, where your function is this. Now next, just do this as your exercise. Find out the poles by putting denominator equal to 0 and find out the residue of the poles which are lying inside the circle and apply the Cauchy residue theorem. Same steps as we have done in the last video in the example. All the steps are same, right? The answer is given to you as pi over square root of a square minus b square. You will get this answer by solving the steps. Next is example 2. This is another kind of an example. Here in the denominator I am having 2. The square power I am having in the denominator. So far we have done with the power 1. Now in this example I am having the denominator having the power 2. Evaluate 0 to 2 pi d theta over a plus b cos theta whole square, where a is greater than b greater than 0. Now here I have to ensure that limit should be from 0 to 2 pi, and it is already from 0 to 2 pi. So there is nothing to do with any change. Just we have to put z equal to e the power iota theta and get my d theta as dz over iota z. Putting this value into this integral and get your integral in z. Whenever we put the values in the integral, this limit 0 to 2 pi will erased and we will write here c, which denotes that this is your circle C. So this is equal to 1 over a plus b by 2. That means your cos theta will be changed into 1 by 2 z plus 1 over z whole square, because The denominator is having the power 2 here, so square comes up here, and d theta is, this is dz over iota z. When you solve this denominator, you will find minus 4 iota as in your next step, integration z dz over bz square plus 2az plus b whole square. And this integral, you just take all over this as your function fz dz, where this c is the unit circle mod z equal to 1. Now the next step is we have to find out the poles by taking denominator equal to 0. So this denominator bz square plus 2az plus b is equal to 0, and this is your quadratic equation. You will get your roots as z is equal to minus a plus minus square root of a square minus b square over b. Right? Now take one of the root as your alpha and the other root as beta. So alpha is minus a plus square root of a square minus b square by b, and beta is equal to minus a minus square root of a square minus b square over b. So these are your two roots, and these two roots are nothing but the poles of fz. Now you have to check whether these poles lies outside the circle or inside the circle. For that you need to check the mod of the poles, right? Since a is greater than b greater than 0, therefore if you check mod of beta, then this comes out to be greater than 1, right? And since the product of the roots and their mod is equal to 1 and mod of beta is greater than 1, your mod of alpha should be strictly less than 1. I have solved this in the previous video. You can check from that how this mod alpha is strictly less than 1 and how this mod beta is greater than 1. Now because mod of alpha is strictly less than 1, that means this alpha lies inside the circle, because your circle is mod z is equal to 1 and this is less than 1. So alpha lies inside the circle, and because mod beta is greater than 1, beta lies outside the circle. So we need to find the residue of fz at one pole only, that is alpha. So z equal to alpha lies inside the circle. So z equal to alpha is the only pole of order. Now what is the order of this pole? See, the denominator is having square. So obviously the pole of this order, this pole is having the order 2. It's not a simple pole, right? Now f of z is equal to minus 4 iota z. We have taken this f of z as, take the leading coefficient outside b square and write z minus alpha whole square and z minus beta whole square, as these are the only two roots of the quadratic polynomial. Now we have also read the remark that to find the residue of the function at alpha of any order, suppose order k, then the formula for that is 1 over k minus 1 factorial, and we have to derivate z minus z naught the power k f of z k minus 1 times. Now here the pole is of order 2. That means here k is equal to 2. So we have to first only derivative, we have to take the derivative of this once. We have to derivate once because k is 2. So this is 2 minus 1, that is 1. One time only you have to derivate. Just put here the value of k as 2 and solve further. So residue of fz at alpha is equal to 1 over k minus 1, that is 2 minus 1 factorial, limit z tends to alpha d by dz of z minus alpha whole square into f of z. Write down the value of z over here in the next step. So this is limit z tends to alpha. This is 2 minus 1, 1 factorial, that is 1 only. So d by dz of z minus alpha square into minus 4 iota z over b square z minus alpha whole square z minus beta whole square. Z minus alpha square cancelled out and you will be left up with limit z tends to alpha derivative of this with respect to z 4 iota z over b square z minus beta whole square. Just derivate this, you will get this thing, and alpha plus beta, find out the sum of the roots, find out the difference of the roots, write down their values, and you will be getting this. Now at the last we have to just apply the Cauchy residue theorem. So this integration from 0 to 2 pi d theta over a plus b cos theta whole square is equal to integral c fz dz, that is equal to 2 pi iota times residue of fz at z equal to alpha, right? So 2 pi iota, what is the residue of fz at alpha? We have just calculated, this is minus a iota over a square minus b square. Minus a iota over, is it a square root? No. A square minus b square 3 by 2. Sorry. So a square minus b square 3 by 2. And finally this answer is equal to, this iota is minus 1, so this will be positive 2 pi a over a square minus b square the power 3 by 2. Fine, here ends up the solution. Next, this is an exercise for you. Evaluate the integral from 0 to pi d theta over a plus b cos theta whole square, where a is strictly greater than b greater than 0. All the steps are same. You just have to change this limit because it is given from 0 to pi. So for that, you have to first check the condition that f of 2a minus z should be equal to f of z. Now here, whenever you are getting your cos theta in the expression, then obviously every time the rule is satisfied. You can apply that rule. So integration from 0 to pi d theta over a plus b cos theta whole square, this is equal to, we have to divide by 2 to get the limit from 0 to 2 pi. Rest it's same, 1 over a plus b cos theta whole square d theta. Calculate same as it is the steps you have just read in the first example. All the steps are same, right? Just there's a difference that here only you are having half with this integration, right? Alright guys, thank you. We will meet in the next video. And one more thing, if you want to enroll my course of real analysis and vector calculus, the coupon codes are provided for these courses in the description box. You can check from there and you can enroll that courses. Thank you so much. Goodbye.